my knot in 3 space, and then I've taken, you know, its shadow and projected it onto some two-dimensional surface. This is what you get. And then, you know, I draw these over and under crossings to indicate that, you know, this strand is indeed over this one that goes under. Right? And so this is kind of pictorially how we understand this. And this is also how we sort of study them. So if I tell you that I take the anode and I change it in some way in 3-dimensional space, I can change it and draw a different projection of it where I have done some kind of twist. So you can imagine that, so now I don't have a piece of string with me, but you can imagine you have a piece of string and you kind of make some kind of twist to it. It should be kind of the same knot because I'm not changing anything, I'm just moving it around a little bit. But the kind of projections would be different. Well, maybe. In this case, the projections are different. So here's, you know, one projection, and then I made a twist to it. And, you know, the diagrams look different, but I need to construct or find some kind of rule that tells me that these two are projections of the same knot. Okay? And so there are some moves that are called randomized moves. And so there are 3 randomized moves. I'll draw them in a second. And these moves tell us when two knot diagrams represent the same knot. Okay. So the first move is, so I'm going to draw a diagram like this where I have drawn this dashed circle. So I imagine I have some kind of knot diagram, and I have kind of, you know, zoomed in on a small piece of it, right? That's what I mean by the dashed circle. If something happens outside, then I don't care. So the move is that I change this strand and sort of create a twist like this. Okay, this is what I did. This is what I did. Sorry, here I took this, and I guess now. I took this piece of the knot and I sort of created a twist. Okay. So this is the first move. The second move involves 2 strands. So again, it's the same as before. I've zoomed in on a particular piece in my knot diagram, or a particular part of my knot diagram. And what I can do is I can take one strand and sort of move it over the other one without them crossing. So I'm literally doing this. Okay, I'm moving one strand kind of behind the other, and so the resulting diagram looks like this. Okay. The third move involves 3 strands, and this one is a little bit more complicated. So I have a crossing, and then I have another strand going across and sort of behind everything. Okay. And now, so maybe I'll draw this in yellow. So I want to move this yellow strand behind this crossing. So I want to kind of move it down and sort of pass through this crossing somehow. But it's kind of behind everything. So the picture after the move, after I move the yellow strand, it's going to be like this. Okay. So this is the third move. Okay. So my definition is going to be that 2 knots are going to be equivalent if and only if they are related by some number of randomized moves. And I should maybe say their diagrams. Their diagrams. Okay. So this is my definition of when two knots are equivalent. I'm going to cast their shadow on some two-dimensional surface, and if I can find a sequence of moves out of these three, some finite number of such, relating the two diagrams, then they're the same. Yeah.
When you say casting a shadow, you're preserving over and under?
Yeah, that's right. Yeah, I want to I want to preserve it over and under. I want to remember this information. Yeah, that's right. Right, so erase, maybe I'll actually keep it forever because I was going to draw a picture. So okay, so you can look at these two pictures, and you can show that this projection of some knot is in fact the same as this one. So I guess it would be an exercise to you if you're curious. You can see if you can find them. Okay, so that's, I guess, an example slash exercise for you. Okay, but anyway. Any other questions so far? Yeah.
So all possible complicated moves you could possibly think of are going to be some combination of the Reidemeister moves?
That's right. Yeah. Whatever complicated thing you imagine you're doing in three-dimensional space, they can be represented by that. You take some projection, look at the knot diagram, and then you can find a composition of such moves that would sort of represent the move you did upstairs in three-dimensional space. Okay, and so in general, this is all good and well, but it's really difficult to. I can give you much more complicated. I can draw something random, and it becomes very difficult very quickly to figure out if two knots are different or the same. And somehow in some sense, the ultimate goal here of knot theory is to be able to, classify all the knots. I give you two random knots, now you're supposed to figure out if they're the same or not. That's somehow the ultimate goal. Okay. And figuring out if you can find moves between them or not, like Reidemeister moves, this is not very feasible. So one would like to invent some better way to maybe systematically study knots. So the question is how to distinguish knots. And one possible answer is by using an invariant. So an invariant of a knot. So I realize I've said knots a lot, but I didn't say links. But I mean everything. Whenever I say knot, I could as well mean link. But anyway, an invariant of a knot is a. So let me give this a name first. I of k is so this thing can be different things. It could be a number. It could be something more complicated. So it could be like an integer. It could be a real number. It could be, you know, a polynomial maybe. Or something more complicated. It could be some algebraic structure. Some group, some ring, some algebra, whatever. Okay? But it's something we associate to a knot. Somehow, you know, if you don't know how to think about this, think about a number. But it's a quantity we associate to a knot such that this number, this quantity is the same for two knots that are the same. So if K1 is equivalent to K2, then, hence the name invariant, then the invariant should be the same. Okay? This is what an invariant is. It's some quantity, some kind of structure, something which is the same as long as the knots are the same. Okay. And so you may ask, what's the point? So the point and the idea is that this invariant is easier to study or compute, and so this statement right here, it says that if K1 and K2 are equivalent, then I of K1 is equal to I of K2. So if I take the contrapositive statement, it says that if the invariants are different, then the knots themselves cannot be equivalent. Okay? So I have associated some kind of number or something to my knots, and if I can compute these quantities very easily, I can take two random knots, I can compute their invariants, and if I'm lucky, these invariants disagree. And then I can actually draw the conclusion that these cannot be equivalent. So this is a very common and kind of very successful way of at least showing that something is not equivalent, like that, showing that two knots are different. Okay. And I will focus on this idea of constructing some kind of invariant of knots. And I'll give you an example right now of an invariant that's able to, so I maybe should have said it in the beginning, but if I draw the unknot and I draw the trefoil, these two, I think you can look at them and sort of realize that they should not be equivalent. Okay? But it's another question of actually proving they're not equivalent. But we can prove that they're not equivalent by using some simple invariant. And I'll tell you right now how we can do it. Yeah, any more questions?
You're very good at drawing.
Huh?
You're very good at drawing.
Oh, thanks. I would say I'm not very good. So I don't think I'm very talented at drawing. I can draw the trefoil, but I was struggling quite a bit when I was drawing this other knot. But there's people that are much better at drawing than me, certainly.
You're the best person I know who can draw.
Okay, thank you. I appreciate it. Okay. Okay, so the invariant that I will tell you about is the following. So I will give you a definition and then I'll tell you what the invariant is. So a knot is tricolorable if for any diagram of K, and K is my knot, each strand can be given one of three colors such that one, at least two colors are used, and second, at each crossing at each crossing all three strands either have the same color or all different colors. So what I mean is at the crossing it either looks like this or it looks like this. See if I can use red and blue. So this is the definition, so let us digest and see what it says. So what I mean by, okay, so I should explain first what I mean by strand. When I draw knot diagrams, let me use this as an example. Whenever I have indicated the crossings, I have drawn one strand that's kind of going under and one is going over. Whenever there's a break in a strand, I consider that to be a different strand. So in this picture there are three strands. So there's this one, and there's this one, and there's this one. So there's three strands in this diagram. And here there's only one. Okay? So that's what I mean by strand. And I associate one of three colors, white, blue, or red, to each strand. And then I need to satisfy, I need the coloring to satisfy kind of these two properties. I need to have used at least two colors, and at each crossing it either looks like this or like this. And I guess this crossing could either be kind of all red or all blue or all white. Okay, so this is just a definition of saying that a knot is tricolorable, if this is true. Okay?
Is there any requirement for like consecutive things to have different colors?
Sorry, say that again.
Is there any requirement to have like that? It can't be red, red, white.
That's right. Yeah. So so an example of something that is not allowed by the third thing is this. Like whenever a strand kind of makes a break, you need to choose a different color, and it needs to be different from this one also. Yeah, of course, in this picture I could have like, you can, the colors can be shuffled around, but I think they need to be all different. Yeah. Okay. So here is some example, right? So the unknot, this is not tricolorable because there's one strand, and yes, I did say that obviously I cannot kind of change color kind of in the middle of a strand. It needs to kind of be the same color throughout until it makes a break for a crossing, right? So I cannot do something silly like this. So because there's only one strand, it needs to have the same color, and I can choose which one, but it will still not be tricolorable by item 1. So it's impossible to use at least 2 colors. Okay. And if I change the diagram, I guess I don't change the fact that there's only one strand, and I can make a twist and maybe I can make another twist, or I can make a kind of I can take this strand and put it over this one or something. I can try to create more strands or something like this. So now I created more strands because there are some small pieces here. But because I use kind of randomizer moves, you can maybe check this. This is still not tricolor. Okay. And of course, I mean, these two are the same. I just took the unknot and made 2 twists, and then I moved kind of some strand over and up. Yeah.
For the proof, use some sort of graph theory?
The proof is not, I would not say graph theory, I would say it's, you look at the randomizer moves and check that it's, yeah, I would say this I'll show you in a moment.
Oh.
Yeah. Yeah, for now I'm just giving an example. Yeah, so the statement is that being tricolorable is an invariant, right? Yeah, and I will show you the proof in a moment. You check the moves. So let me show you an example where if I draw the trefoil, it is tricolorable. So for the trefoil, it is tricolorable, and with this drawing you can check that all the properties are satisfied. I've used all 3 colors, so number 1 is satisfied. I've used at least 2. And for the second one, we need to check all the crossings. Either all the strands in a crossing need to have the same color or all different colors. So in this case, every crossing has the property that all 3 strands have different colors. So both of the conditions hold, so it's tricolor. Okay. Yeah, so I mean, this kind of thing is, I guess, maybe that's why you mentioned graph theory. I'm not sure, but there's this problem where if you have a map and you can ask whether you can like color all the regions in the map with using some number of colors. And the question is if 4 can you do it with 4 colors? It has the same kind of vibe to it. Yeah. So anyway, theorem, being tricolorable is not invariant. So if I should be a little bit formal, my invariant is I have a knot and I take some, if I can find the diagram that's tricolorable, then I associate some number, and maybe I say that the number is 0 if it is, I mean, I'm giving it the value of like true false. So maybe 0 if it's not tricolorable and 1 if it is. that's my invariant. And okay, so it's a theorem that it's an invariant. Okay. And here's the proof. Because we define two knots to be equivalent if they are related by these Reidemeister moves that I showed you, it is enough to show that the property of being tricolorable is preserved whenever we do one of these or each of these moves. So we need to check that the property of being tricolorable I use the shorthand R123 for the Reidemeister moves. Okay. So for Reidemeister 1, let me actually use red. So for Reidemeister 1, I need to show that if I zoom in on a strand, so we want to, okay, so let me say, we have a knot, and we assume that it is tricolorable. Now we want to show that the fact that it is tricolorable is preserved. So whenever I've chosen a coloring, I zoom in on one of the strands. It has some kind of color. In this case, red. Now I want to make a twist. But when I make a twist, the number of strands remain the same. So there's only one way to fill in this diagram. I have a red strand and I make a twist, and there's no choice. It has to be red first. Okay. So if this diagram is tricolorable, then this one will as well, and going back and forth. Okay. So under this move, either both of them are tricolorable or both of them are not, because I don't change anything outside of this twist. And nothing happens when I do the twist, like nothing in terms of the coloring.
If it's too in the weeds, no, it's fine. But is it sufficient to just intuitively say that it's that? But did you just say like look at it? It doesn't change color. Or?
Well, yeah, sort of, but I did a little bit more. So it's not only look, it didn't change color, but there's no other way of making the coloring different here, because there's the same amount of strands. Each strand has to be the same color throughout.
It's the same.
And okay, so I need to explain. Sorry, yeah. I actually did create a thing. So okay, let me say that again. I create a twist, and I know that my strand from the top was red, so I start out as being red, and I create a twist. Okay. Then I end up here, and now I'm saying there is no choice what to do next. I can purposefully create something which is not a coloring, but maybe let's not. What?
It contradicts the bottom being red and the other one.
Not necessarily. I can do this, but this will automatically make this not tricolorable. I want to change it in such a way that the rules are satisfied. And I'm saying the only way of doing that is to continue at being red, because in this crossing it's kind of red here and red here, and it has to either be all three different colors or all three the same. Because two of them were the same, the third one has to be the same as well. That's all. So let's look at the next one. So in the next one I have two strands, and maybe they have different color. And now I want to move one over the other. And so maybe I move the... well, actually, let me do the easy case first somehow. let me do both of them the same color. So there are different cases that I need to consider. The strands can have the same color or not. In case they have the same color and I move one over the other, so I have one strand here, and then I have another strand here that needs to go under. But then I want to construct, draw this diagram so that it is still a valid coloring. But because in this crossing, there's, again, this strand and this strand are both red, so the third one has to be red. And then I come to the next crossing and the same thing is true. Two of the strands are red, so I need to continue as being red as well. Okay. So again, I'm saying that to have a valid coloring, there's no choice. I just put the strands over one another. Okay, and then you can look at the other case that I mentioned. Well, the other case is there are two different colors. Okay, so now I move the white strand. I move the white strand over the red one. Okay. So now, in this crossing that I'm about to draw, there's two different colors used, which forces me to use the third color if I want to remain a valid coloring. Okay, so I change color to the third one that I haven't used yet. And then I come to the next crossing, and the same is true here. I have two different colors already, the white and the blue. So the next one has to be red when I continue, if I want to remain being a color. Okay. And those are the only two cases to check here. So what this shows is under Reidemeister 1, so if this diagram is tricolorable, I do this move and it's still tricolorable because outside of this dashed circle, everything remains the same. And the only thing that changes is here, and so I only need to produce a tricoloring of this diagram inside the circle. So it works in the Reidemeister 1 case and in the Reidemeister 2 case, in the both cases that we need to consider, so the strands can have the same color in the beginning, like when they're separated, both of the same color, and then I can do it. And when they have different colors, I can also do it. Okay, and then you can check the third move as well. It's not much more complicated, but there's some more cases to consider. So the easy case is when all the strands have the same color, and the other case that is more tricky is when all the kind of strands have different colors. And now I kind of need to be a little bit careful, because now I can do it in the wrong way. Okay, so I think this is a valid coloring. So at each crossing, all three colors are being used. Okay, and now I want to move this strand that's kind of behind everything, and I want to move it across the crossing here. And so the white strand is kind of at the top, and then I have this blue strand, here, and then I have this horizontal one that I want to move down. And so now in this picture, I probably want to use white here, and then blue, and then red. Okay.
Well, that's not the same because the white was over there, now the light is over there, the white and the red switch places with the white strand.
Yeah, and then more to there's blue that appears in the numbers. Is it about
That's right.
maintaining that it's either follows or doesn't follow it? Tricolorableness?
So again, either it follows or it doesn't.
Or it doesn't follow tricolorableness? Oh, actually, oh wait, yeah, there's two lines in a row. 1 second, sorry, great.
So that's just one strand.
Oh, sorry, yeah,
Oh, okay.
I think I was wrong.
Is that right?
So I still think this is, yeah, so yeah, I mean, one has to say something more, but this is the idea. I mean, the kind of, as you said, the blue kind of changed to being white right here. And the same with the white and the red on the outside. So in this strand, yeah, I mean, you have to say something more to complete this, but this is the idea. It's more complicated.
Question about the R2, that second diagram.
Yeah.
So we can just have the colors change? Like
Yeah.
that, the first one's not tricolorable, right? Because there's only.
Well,
two
I don't. No,
colors.
no. The first one. So tricolorable means like the whole diagram, and I only showed you what it looks like inside this small circle.
Okay.
So I could have. Yeah, this picture could have been. So I don't know where. Yeah, here. This picture could have been, you know, this piece of the trefoil, and outside it does something. Yeah.
Can you show an example of a tricolorable knot where only two colors are used?
Yeah, okay, I can, I don't know, yeah, take the whole thing that I showed you. Yeah, okay, so let me, I was not intending to say anything more about the picture. Yeah, so the example, I mean, yeah. So luckily I allowed myself to use links, but right, okay. So this is of course not okay. So let me try to think.
Could you technically have two separate circles? Does that count as a link?
Yeah, of course. Yeah. Good. Thank you. Yeah. That's the valid. It's a valid tricolor. Yeah, that's right. Yeah. Great. Yeah. Yeah, okay, not enough. Try to find another. Yeah. Okay, but with this theorem now, yeah. With this theorem, we can draw a bunch of conclusions from these pictures, right? So we have shown that being tricolorable is a knot invariant, which means that if we can find two knots so that one is tricolorable and one is not, it means that the knots cannot be the same. And so because the unknot is not tricolorable, and so this is called the unlink. This is tricolorable. These are not the same. And this is somehow obvious. One contains two circles and the other one contains one circle. It also shows that the unlink is not the same as the hop link. So we have the trefoil. This is tricolorable and unknot is not tricolorable. So it shows that the unknot and the trefoil are not equivalent. And I guess that's all the examples we saw. Yeah, okay, so the hop link is also not the hop link. Sorry, the hop link is not the trefoil. Yeah.
Can you, so you're saying it's invariant, right? Tricoloring.
Yes, that's right.
But so does that mean that any knot that is tricolorable is equivalent to tricolor?
No.
Yes.
It's the other way around. Yeah, so if two knots are so that one is and one is not,
I see. So it's
then they cannot be the same.
right.
But observe, this does not go both ways. So it can only tell us, yeah, it can only tell us when two things are different, well, potentially. So for instance, this cannot tell us whether, yeah, so the unknot and the hop link, both of them are not tricolorable, but somehow obviously not the same because it's one less component than the other. So the hop link and the unknot should obviously not be the same, but we cannot use this invariant to show it because both of them are not tricolorable, so it doesn't make us able to draw any conclusion. But they're obviously not the same. So, but you know, to prove that they are different, one has to use a little bit more, some more complicated invariant. But this is just sort of the one of the simplest ones, rather the simplest one. I don't know. Yeah.
So if you have like a tricolorable knot and then a not tricolorable knot, if you remove a link from the not tricolorable knot, will they still both like necessarily not be the same?
So I did not quite follow. So if you have two, you said you have two knots,
Yeah, you have
or
two
let's say
knots.
two links or something,
Yeah.
and you remove some part of one of them.
Yes.
So wait, so you wanted them to be. So can you repeat what you said?
Okay. So you have one knot that is tricolorable,
Yeah.
and then you have another knot that is not tricolorable.
Yeah.
So you can make the assumption that they're not the same knot.
Right.
If you were to remove like a link from one of them, will that assumption remain, or is it possible for that assumption to change?
Yeah, you mean tricolorability.
Yeah.
Oh, this can change.
Okay.
Yeah, I mean,
Take the one circle and the two circle one. And then if you remove one circle from the two circle, it's just become the one circle one, right?
Oh yeah, this is tricolorable. Yeah, that's right. Yeah, take this one and remove one. Yeah, that's right. Yeah. I was imagining. Yeah, I was trying to take the trefoil and do this or something. Add another component to the trefoil, and now it's not tricolorable. But if you remove it, it is. Or something. Yeah, that's yours. Something similar. Yeah. Okay. Okay. So now I will try to say something about Legendrian knots in 7 minutes. Okay, so in knot theory, yeah, okay. So now I could have given you some other invariant or something and said that we study knots and using some other invariant, and that's all good. So one can also kind of study knots that satisfy some kind of geometric constraint, and these are what Legendrian knots are. So I will tell you what we're going to do now. So we're going to take our three-dimensional Euclidean space, and we're going to equip it with a plane field and this plane field I'm going to denote it by C. So our plane field is sort of like a vector field. We imagine that in three-dimensional space I have a plane, and this plane is going to be different at different points. And at the point x, y, z, there's going to be a plane that's going to be the span of these two vectors. So at every point x, y, z, I take the span of these two vectors, and this gives me a plane. this this only depends on y. Okay. Okay. So now the definition is that a knot, let me call it K, is called Legendrian if it's everywhere tangent to C. If it is tangent to C, X, Y, Z for every X, Y, Z belonging to my knot. Okay, so this seems like a very artificial and weird condition to impose. So that's somehow true. So so I guess this is now some advertising if you're interested in actually reading more. This is called a compact. So C is called a compact structure. Okay, so these have some names. But we can this definition can be kind of realized in a different way. If we pick a parameterization of our knot, so I parameterize my knot, then K being Legendrian is the same thing as imposing that the y coordinate is the quotient of the time derivatives of the z coordinate and the x component respectively. So in this condition that you're being tied into this kind of weird plane field, you're imposing kind of constraint that if I specify x and z, I can kind of specify y by taking some derivatives and kind of calculating what the third coordinate is supposed to be. It's some kind of weird condition that your knot needs to be kind of tangent to some plane field. And there's a particular projection. If I project to the x, so there's two projections. The first one is to the xy plane, and the projections of these knots will kind of look a little bit weird because I have restricted amounts of freedom. So the projection of the unknot will need to look like this. I cannot untwist this twist in the unknot, and the trefoil needs to kind of have the trefoil needs to have kind of 2 extra twists in it, and I cannot undo them. And there's this other projection that you also study, which is to the xz plane, and this projection is even more weird because I allow there to be kind of some weird cusps going on. I cannot have any vertical tangent lines. I will have these kind of cusps instead. And it's actually possible to see that these two are the same thing from different perspectives somehow. I mean, okay, I will not try to attempt to. It's possible to see it. I mean, I'm not very good at seeing it, but yeah. And so here is the trefoil. In any case, these are just pictures to waste a minute. But the Legendrian knot story is very interesting and very kind of, it's some story that comes from it's motivated by physics why one, would ever consider these kinds of weird plane fields in 3 space and so on. And it's also related to a field called symplectic. It's called symplectic geometry, which is also it's related to this contact structure business, but it's also related it comes from physics. There's very good reasons to study these things and to consider these restricted kind of knots where you need to be tangent to these things. And yeah, anyway, I think the main part was about the knot theory, and I don't have much more to say.
Very interesting.
Yeah.
Are there any invariants that do have a bidirectional relationship?
Oh yeah, there are. Yeah, so they're a little bit complicated though.
Like I was just looking for vocabulary.
Oh, okay, sure. So you can so if you want vocabulary, then so you mean what these invariants are called? Like
Yeah.
they call a complete invariant.
Oh, yeah. That makes
But
sense.
I can give you an example. So if you have a knot in R3, you can consider the complement. So you can consider 3 space after you carve out the knot. Okay? And then you can consider what's called the fundamental group. Okay? And this is somehow homotopic classes of loops in this space. Somehow loops up to deformation somehow. Okay, this is still not a complete invariant, but you need to kind of extract something called a peripheral subgroup. Anyway, like this is called a knot group. It's some kind of algebraic structure, it's a group, but you take the complement and look at how loops look in the complement, and then there's something called peripheral subgroup. But these two together, they form a complete invariant. But of course, like when you're a complete invariant, this is like almost impossible to compute. If I give you some knot, I mean, yeah, this is like nothing you would compute on a Thursday afternoon. So, but yeah, so, okay. Anyway, they are complete invariants, but they are kind of very complicated as they should, because like knots are complicated. Yeah, the dream would be to have a complete invariant that's very easily calculated. So I think it.
Right, because the singularities and the same, like the same sort of hyperplane in, like R3, or like we have to change the coordinators to match this one to that one if they are in the same shape, something like that, right?
So you're thinking about.
Yeah, like let's say we have 2 different knots.
Yeah.
Such that group, they are the same, they are, their invariants are the same.
Yes.
Then they are like, they are like 2 hyperplane that is like, like let's say this one is a curve like this,
Yeah.
that is smooth and like has no singularity, then the other one should be, smooth, no singularities, something like that as well, and there's a strength coordinator between them, right?
Yeah, I mean, so in all of these, yeah, so in this case, I was not thinking about the Legendrian. So this is just by the regular knots that I was talking about. Yeah, and if K1 and K2 have the same, if this is the same for both of them, it just says that they are equivalent. But they have to be like smooth and like, there's a deformation from one of them into the other somehow, and there cannot be any singularities on the way from one to the other.
Is there any way that we can, extend this to other space as well? Like, maybe not on 3, maybe like,
Yeah. Yeah, so basically everything I mean, you can replace R3 with a 3-dimensional sphere, which is what you take the clear space and add a point at infinity. This is fine. This is, then everything I said is true still. Everything is fine. But if you do something more complicated, some more complicated space than R3 or S3, then the answer is more complicated for other reasons. Like if you consider,
Like the projective space, for example, this will be contracted.
yeah, this would be maybe even more. I was going to say something simpler. Like if you take a 2-sphere multiplied with a 1-sphere, then I mean, somehow if your space it's so. In 3-dimensional space, the unknown, you know, it's the kind of it bound. You can draw a disk with boundary on unknown. But if you live in some other space, such as this one, you can draw a circle in this space. So you can draw like an unknown, but it's not obvious. It's not true necessarily. If your unknown kind of goes around this S1 factor here, you cannot fill it with a disk.
I still couldn't like figure out the shape of this space.
Yeah, no, it's not. No, I mean, yeah, no, it's not something you. Yeah, it's not easy to visualize. But yeah, I'm saying if you have more complicated spaces, the null theory is sort of more complicated, but the essence is in some sense the same.
Oh, an example of that one should be the half vibration, right? Like the
Yeah, so that one goes from S3 to S2 maybe.
you know, I mean the group things like below it, like if you have the half link, like the two half links, then yeah, like they kind of have the same group, and should be the same.
Yeah, if you have, yeah, I see. You take half, or you're saying something like the half vibration, then you take two fibers, then it would be a hop link.
And yeah. For the projection into plane X1,
Yeah.
can we have somewhat the same projection into, like, let's say, like YZ, and like move it here from Y is the same image?
Yes, you can project to YZ, and honestly, I don't know what that projection looks like. I need to think, but okay. So for this contact structure or contact geometry story, you basically only consider projection to XY or projection to XZ, like very specific projections. Yeah, it's because like your knot is very rigid in space, not very rigid, but it you know, there's a kind of constraint, and if you start to project onto some random plane, it's very difficult to control what happens because you have some very specific condition on this knot, precisely this condition, and if you now project to some other random plane, it's not very easy to draw. But if you have no conditions, such as in the story before, then I can just draw some picture. But now it has a kind of very specific constraints, and so one loses some kind of information. Well, I mean, I guess we choose to kind of work with these two projections, and those are the ones that sort of give everything. Yeah.
Could you say a little bit about the application to physics that motivates Legendrian knots?
Sure, yeah, so there's, I wish I had like some, one can do like a lab experiment, so okay. Yeah, so there's some kind of relation to optics that where if you look at reflections of light and project like projections of light onto a surface, the curves you see on the surface. I think if you take a regular drinking glass and shine a bright light on it, then it will kind of make light reflect in a certain way. And if you look at the reflection of the light, maybe cast on a table or something, these kind of wave fronts of light will have shapes that kind of look like this. Yeah. They will have these kind of cusps and stuff, sort of like this. And so there's a connection between contact geometry and the kind of geometric optics where you would consider wave fronts of light and projecting this to kind of some surface. So I would not say there's maybe no by solving some problem in here, I don't know anything about physics, but so I don't think I am solving any problems in physics. But it's of course more, the field of math was originates from some kind of study in physics, and then mathematicians work on it, and then it kind of develops into its own thing. So it kind of comes from there, and you study it because it's worth studying on its own. Any other questions?
Also, you left us a bit of a cliffhanger with the Riedmeister 3 preserves. What's it called? Preserves tricolorability.
Oh yeah, let me dodge that. That is
How hard is it?
It's an exercise.
Okay.
It's an exercise to work out. Yeah, it's not supposed to be very difficult. I may just messed up. Yeah. Yeah, let me just do it as an exercise. I don't think there's anything.
Okay.
It's not that interesting, I drew it out.
Yeah. Okay. Great.
There's like 4 cases.
Yeah.
The presentation I call it.
Okay.
If we do have like bidirectional invariants, then why can't we categorize all different knots?
Yeah, good question. Because those invariants that are complete invariants, they are very difficult to compute.
Oh.
So good luck. Yeah, no, I mean, yeah. I told you this was an invariant, but like if I give you some random knot, it's impossible to compute.
Oh.
It's a theoretical thing that you can show that it must be a complete invariant. It's a very hard theorem, a very deep theorem, but no one is able to compute it. I mean, I think people knew from. I mean, this was proven to be a complete invariant in 1960 or something like that, which is some time ago. If this was sufficient to kind of close the field of knot theory, then somehow there would be nothing else to do somehow if this was somehow computable. Of course, it's not. Yeah.
So far from the definition of the K, so K cannot have any links, right, like this?
Yeah. So here I maybe. Yeah, sure, but it was just a flaw in how I wrote this. You can imagine K can have more components. Just so define. Take multiple of them. Take one parameterization for each circle, and then each component satisfy this thing.
Okay, and then you just link them.
Yeah, they can be kind of linked in three-dimensional space. Absolutely, That's no problem. Yeah, I mean the Hopf link would look like 2 copies of this like linked together, and you would have. A drawing this sort. You would in this projection it would look like 2 copies of this just linked together. In this projection it would look like this or something.
By the way, I think we're also interested in the homotopy group of the complements, right? So if we have for example 2 knots with links, well the homotopy group the difference with the homotopy group of the complements of 2 knots with some links.
So can you restate the problem? So if you have 2 knots,
like if you have 2 knots K1 and K2, there might be either links or unlinked, right?
I see, yes. Yeah, okay, I see what you mean. So if you take, you can look at this situation, or you can look at this as being separate, and you want to take this to be K2 and the other one to be K1, and now you're asking, let's look at the pi 1 of the complement or whatever, for example. Yeah, they would be different, I think, I mean, for links, there's actually maybe like an easier maybe an easier invariant than the tricolorability. So for links, you can, you can define something called the linking number, which is basically you give the components names, and then you check how many crossings there are between the components, and you divide that by 2. Because if you have different components, they must link an even number of times. So here they link, or they kind of have 2 crossings, but maybe I want this to kind of have, so sometimes we also put like orientations on the link, so I give each of the components like a direction. And now I maybe will count this crossing to be +1, and I count this crossing to be -1. And so maybe now I can define the linking number to be like the number of crossings with sign divided by 2. And so the linking number here would be plus or minus 1. I can't be bothered to check which sign. So it's either plus or minus 1. And you can show that the linking number is an invariant. And so and you can show, so this has linking number plus minus 1, and the unlink has linking number 0 because there's no crossings between the components. And so then this is the difference. That's like, maybe easier, but that can also be used to show that these are different. And so I guess that can also be used to show that these are different, because here the linking number is 0, and when they're linked, they have linking number 1, or plus minus 1. Yeah, so typically there are usually easier kind of intermediate invariants, such as linking number or something, which is easier to compute. Than, you would really want to avoid computing this. Yeah, even if you take the trefoil, which is like the simplest knot, which is non-trivial. Even the complement of the trefoil knot, like pi1, it is like very interesting group. So even in the kind of very simplest case, it's kind of some very interesting algebraic structure that appears. But yeah, of course, there's. If I had infinite time, I would tell you about some other invariants that are very powerful and also sort of easy to define, which is much easier than this, but they're kind of interesting. So I can give you names if you're interested in all. Like there's something called the Alexander polynomial. And there's something called the Jones polynomial. So both of these, as the names suggest, they're polynomials. But these Alexander and Jones polynomials, they're very combinatorially defined. I mean, they're basically defined using pictures, and it gives them kind of polynomial. And these 2 guys are very, it's something that I could teach you how to compute in 1 hour, and there are like open problems about these things, which are. Which people don't know how to solve, that are very difficult. But these are kind of very good not invariants and can distinguish a lot of invariants and so on. But very easy to define. So somehow this is a very good invariant in the sense that they're easy to compute and seem to know a lot about knots. And there's kind of unknown things that we still don't know about these things. But yeah, anyway. So if you're interested, then you can Google and read about these. It's very interesting. Any other questions?
Okay, thank you very much for giving the talk.
Yeah.
Thank you.